All right, so let's provide a summary and preview what's going to happen next time. So the thing that we really did here was that either your surface S is described one way or another. It's either described in a parametrized fashion here, parametrized, or, and it's not really all that different, it happens to be the graph of a function that we've been calling lowercase g of x comma y. So function lowercase g of two input variables x and y. So those are the two ways that your surface can look here. So if we write out the parameterization as r of u comma v, but write this in the form of a vector function, the first formula x of u comma v, then comma the second formula y of u comma v, and the third formula z of u comma v. Okay, for the points u comma v in D, where D is the parameter domain. Okay, that's how the surface itself is described. Or on this side, where you have the graph of a function, we could go ahead and mimic what we just see here. It's really just a special case, and you can have r of x comma y equals angle bracket x comma y comma, well, the z formula is just g of x comma y. Here there ought to be a parameter domain as well, so for x comma y belonging to or in a set D. Again, D itself here is the parameter domain. Okay, and then in this setup over here, in the parameterized surface setup, the area of the surface is given by the double integral over D of the magnitude of r sub u cross product r sub v, close magnitude, d capital A, where dA is either du dv or dv du. From here we had derived, and I don't mean differentiated, I just mean we obtained, we proved rather that there's a special case where over here the area of the surface S is just looks real similar because it came from over here, and it's the double integral over the parameter domain D of, it worked out to be root 1 plus partial derivative of g with respect to x squared plus partial derivative of g with respect to y, quantity squared, and then there was a dA here where now dA is either dx dy or dy dx, or if you get a little more fancy, perhaps it's even an r dr d theta, but let's not go there. Okay, so we either had this area formula, which works in general, or this area formula for the special case where the surface was the graph of a function. Now, next time, more generally, we're going to define a thing called a surface integral. We haven't really actually done that yet. Okay, a surface integral. So what's involved here is now we're going to be given a function, lowercase f of, and it's important, it's going to be 3 input variables, x comma y comma z. By the way, because we in the next section needed this lowercase f, that's why you might have been confused or puzzled why we were using a lowercase g here. It's because we could have both a lowercase f and a lowercase g. In any case, it's important for f to be a function of 3 input variables. And what we're going to do is we have this function, and we are going to make sense of, next time we are going to make sense of the double integral over S, over the surface itself here, of f of x comma y comma z d capital S. Now, okay, we're not going to define this right now, right, or even really talk too much about what it means, but to try to give a little bit of a preview, we're going to define this in such a way. We'll define this, okay, the integral that's in the box here, in such a way that if the function were 1, okay, if this function in here were just the constant function 1, so that the double integral over s of 1 ds, we're going to get this to equal the double integral over d. We're just now copying the integral that's over here, of magnitude of r sub u cross product r sub v dA, and then over here the double integral over s of 1 ds is going to equal double integral over d of root 1 plus partial derivative of g with respect to x quantity squared plus partial derivative of g with respect to y squared dA. Okay, so we have these integrals over here, sure, but they're just special cases of this type of integral that we're going to define next time, where what do we mean by special case? In the specific scenario we have, notice the one that's right there or the one that's right there, we're dealing with as our warm-up case, the situation when the function f of x comma y comma z is just equal to 1. You just have this constant function. But next time we're going to talk about what to do if you didn't have a constant function, if you had any old function for f of x comma y comma z. So it will use a lot of the setup that we have here, and so finding just the areas of the surface using this integral or setting up that integral is a good warm-up to what we're going to be doing next time.